Okay, so anytime you're simplifying roots, you're looking for, and in these cases, since they're all square roots, you're looking for perfect squares. So a list of perfect squares really quickly at the top: 4, 9, 16, we get the point, right? 81, 100, what's next? 121, it's 11 squared, 12 squared is 144, and then so on. You should definitely know up to the 12 squared, if not up to 15. And then those are just the numerical perfect squares. From a variable standpoint, what does the exponent have to be in order to have a perfect square root? Even. Very good. So x squared, x to the 4th, x to the 6th, and so on. Okay, so when we're simplifying, the format, the way I write it might be different than the way you're comfortable from your past experience writing, which is fine. You can do whatever works for you. Root 500, you always want to find the biggest perfect square that goes into that, okay? If you don't find the biggest perfect square that goes into it, you're just going to have a couple different rounds of simplifying that's necessary. So just like when you simplify a fraction, you want to find the biggest or the greatest common factor that goes into two numbers. Let me do this for example, 24 divided by 32. If I'm simplifying that and I know those are both divisible by 2, I would make it 12 over 16. But because 2 wasn't the greatest common factor, this still is not fully simplified, right? And I have to keep, dividing out common factors, versus if I right from the get-go pull out the greatest common factor and divide that out, which is 8, that would immediately become 3/4 and I'd be done. Versus here I could keep dividing by 2 and 2, and it would take me a couple of rounds to get to the final answer. So it's not that it can't be done, but it's going to make your life a lot faster if you find the biggest perfect square that goes into 500, which is 100. So I would break down this into root 5 times root 100. And then you can actually apply the square root. The square root of 100 is 10. And so we get 10 root 5 as your answer. Okay? When you're multiplying multiplying radicals, I recommend you multiply them first, then simplify. So root 6x times root 3x is going to be root 18x squared. And then the biggest perfect square that goes into 18 is 9. So we have root 9, root 2, and then x squared is on our perfect squares list, so we don't need to break that down at all. We're just going to leave that x squared. So there are a couple things, and I like to circle what you're now allowed to take the square root of. The square root of 9 is 3, and the square root of x squared is sort of. We're going to come back to that one. I got one new thing to teach you. So you guys, at this point, would put 3x root 2. Okay, but we're going to update that in a little bit here. Number 3, you're taking the square root of a fraction. You do the numerator and denominator kind of separately. Root 100 over root 9 is how you kind of process that mentally, and we get 10 over 3. Any questions there? Okay. Number 4, how would we break down 48? Think about that. Zach, how would you break down 48? Root 16, root 3, good. How would we break down x cubed, since x cubed is not on our list? It's not something we can take the square root of. Yep. Right, root x squared, root x. So in the numerator, I'll be able to take the square root of those two pieces. And then in my denominator, I really can't do anything, yes? Root 6x. So I get, on my numerator, a 4x root 3x over root 6x. Now, what do we think about this? Because we can go further. Connor?
You can split the root 6x into root 3x and root 2.
So if I were to split that up, if I were to go back here and split this into root 3x times root 2, or you want to do that here?
Either way.
Either way. And what's the benefit of that?
Then root 3x cancel out.
Right. Very good. So 4x divided by root 2. Now, did you guys, you did, talk about rationalizing, not being able to leave the radical in the denominator, right? So what would I have to multiply by to kind of rationalize this? Radical 2 over radical 2. So we end up with 4x root 2 over 2. And then I can reduce this how? Right, 4x divided by 2 is 2x. So I'm going to really kind of wrap this around because I had a lot of steps. 2x root 2. We just divided 4x divided by 2. Now, how could I have done this much faster? Nathan M. Right. So just like up here, we separated it into 2. This one started separated into 2, but we could have kind of condensed it into one fraction first, simplified that one fraction right out of the gate. So 48 divided by 6 is 8. X cubed divided by x is x squared. And then just simplify that. Wouldn't that have been easier? So that's root 4 times root 2 times root x squared, which is going to make your 2, your x, and your root 2 that we ended up with anyway. So there are ways you can make your life more challenging, and that's what we did the first time through, and obviously, therefore, the bright side, there's ways you can find efficiently to do these so they take a little less time. But either way, you're following good principles, and you'll get the right answer. Number 4 is star 2. We will come back to that because we're going to clean up that final answer too with a new concept. Number 5, adding radicals is almost like adding and subtracting fractions. Okay? You need a common denominator when you're adding and subtracting fractions. You need a common radical in order to be able to quote unquote combine like terms, combine like radicals. So as this is right now, not combinable, but we can simplify the root 12 into 2 root 3. And 7 root 3 plus 2 root 3 is now 9 root 3s. So when you are adding and subtracting, simplify first, then combine like terms. Okay? Versus multiplying, I like to just multiply first and then simplify, because there are moments where if you simplify from the start and then multiply, you just have to simplify again. So I like to, with multiplication, I like to get multiplication out of the way, just multiply it right out of the way, and then simplify. That way you only simplify once for sure. With adding and subtracting like radicals, you don't have that luxury. You simplify first. Any questions? Okay. Now on this one, You do it one of two ways. You can rationalize it right out of the gate and go from there, or you can simplify it right out of the gate and go from there. Why don't you take a minute or two to do that one on your own, either way you prefer. Simplify and then rationalize, or rationalize and then simplify. And we'll hope we all end up at the same spot. All right, where's Michelle? Hi, Michelle. Michelle, what did you do first? Okay, so she chose rationalizing first. She got 12 root 8 over 8. Then what'd you do? Okay, then what? 12 times 2 radical 2 over 8. Keep going. Very good. Nice. Okay, did anyone simplify first? Taylor, what'd you get? Right, but when you simplified first, you got 12, and then you did root 4, root 2?
Yeah, and then that is, I think we started with 4, so it's 2 radical 2.
Yep.
And then I multiplied that radical 2 over radical 2.
So you didn't really fully simplify. You didn't do the 12 divided by 2 right away.
No, I didn't.
Okay, so you left that, then rationalized, got 12 radical 2 over 2 times 2, which is 4.
Yeah.
And then got 3 radical 2 that way. Good. Or you could have just made that a 6 right on the spot. 6 over root 2. If she was here, she could have done 6 over root 2 and then rationalized. So it would have been 6 root 2 over 2, which would be 3 root 2. So obviously several different ways we get 3 root 2. Okay? I'm going to put a dot, dot, dot after that because we wouldn't be done. All right? How do we handle 7?
Difference of 2
I think you're sort of on the right page. Jalen? By the conjugate. Very good. So we're rationalizing. Now, rationalizing a monomial, you just multiply by whatever that radical is over itself. Rationalizing a binomial that contains a radical, we multiply by the conjugate over itself. So 5 minus root 3 and 5 minus root 3. Okay? So what will always happen on your denominator is because they are conjugates, your outer and your inner, when you distribute, will cancel. So you get 25 when you, do you guys know the term FOIL? Okay, so when I say outer and inner, that's like the inner two multiplications of FOIL. Your outer is going to be negative 5 root 3. Your inner is going to be positive 5 root 3. That's the beauty of conjugates. Positive 5 root 3 and negative 5 root 3 will cancel, and then you just have your last two terms to worry about. Positive root 3 times negative root 3 is just negative 3. So there's your denominator, which will be 22. And your numerator, when you just distribute, you're going to get 35 minus 7 root 3. So your final answer, 35 minus 7 root 3, all over 22. Any questions on that? Good stuff, remember that? Okay. Okay, here's the question of the hour. What's the square root of negative 4 squared? What do you think, Jack? 2 radical 2. That wasn't an anticipated guess on my end. Where'd you get that from? What's negative 4 squared? Think about that again. 16. Connor, what do you think?
Positive 4.
Positive 4? And the other logical guess is negative 4. So which is it? Raise your hand if you think it's positive 4. Raise your hand if you think it's negative 4. So I see where everyone's coming from, right? The positive 4 people are saying what Jack said. Negative 4 squared is 16. Square root of 16 is 4. Yes? I see what the negative 4 people are thinking because they're like the square root and the square cancel, right? So, the answer is 4. Okay? The square root and the square canceling is only partially true. So this is why I put a little star next to number 2 and next to number 4. Jump down here to this little section here. The square root of x squared, what do you guys think that is? X. And unfortunately, you'd only be right half the time, because in this case, what's in place of your x? Negative 4. Is your answer x? Is your answer negative 4? No. So the reality is that the square root of x squared is not always just whatever that value x is, as we saw right here. It's not just negative 4. Those don't just cancel. They sort of do. But the reality is, based on order of operations, we always square first. So if x is a negative number, when we square it, it's going to become that positive 16. And then the square root of that 16 is a positive number. So the square root of x squared does equal x if x was positive to begin with. But if x was a negative number to begin with, it's going to be the positive answer. So what you'll see in your answer key at times is that the square root of x squared is the absolute value of that number or that variable. Okay? This little finicky piece that you've never seen before only comes up when you have an even exponent and an even root. So it can come up when you raise things to the 4th power as well. They both have to be even, and if they are both even, you need absolute value signs around your variable. So go back to number 2, where we took the square root of x squared. That actually should have been the absolute value of x. And that just protects against the what if x is a negative number kind of scenario. Because if x is a negative number, again, and you square it, it becomes positive. So the radical of it will have to be positive. And same thing in number 4. We did the same thing right here. The square root of x squared should be the absolute value of x. Does it make sense as to why we need that? It's kind of a new concept. Any questions on that? Okay. What is the difference between popular question, these two? If someone said to simplify this, what's your answer? 4. If someone said to solve this, what's your answer? Good, okay. When you are taking the square root of both sides in an effort to solve, you always have to remember the plus or minus. This is called the principal square root. Okay? The principal square root. So when you just see something and it says, what's the square root of 16? You would never say negative 4. The square root of 16 is 4. Principal square root. There's an assumption there that we are only asking for the principal square root. Versus when you're taking the square root of both sides in an effort to solve, you have to remember that a positive 4 squared could have given you 16, or a negative 4 when you squared it could have given you 16. Okay? And more on this rule over here. If n is even, right, x squared square root, the absolute value of x is your answer. If n is odd, we don't need it. Okay? Because, let's take for example, if we do have a negative number and we cube it and then look for the cubed root, it doesn't really apply here because when you cube that negative 2, what do you get? Negative 8. And the cubed root of negative 8 is negative 2. So what your x value was is in fact your answer when you're dealing with odds. Okay? Odd roots and odd exponents. I'll be honest with you. Not going to come up often, but if and when it does, it's kind of a new thing that, you know, through Algebra 2, it's not worth the hassle of explaining it to you now that you get to a more upper level. We kind of tell you something we've been withholding from you all this time. Okay? It's kind of like in Algebra 1 when you took the square root of a negative number. No one told you about the whole imaginary concept, right? They were just like, oh, square root of a negative number, you can't do that. So we can't do that, no solutions. But there's a whole other world of imaginary numbers out there that we let you know about in Algebra 2. Okay? All right. So when we move up to fifth roots, fourth roots, third roots, we need to know what the perfect cubes are, the perfect fourth roots, and so on. So just really quickly at the top, your perfect cubes. What's 2 cubed? 8. 3 cubed? 27. 4 cubed? 64. 5 cubed? 125. 6 cubed? Okay? And then we lose track a little bit earlier than we do with perfect squares just because the numbers get larger faster. As far as variables are concerned, what about a variable would make it a perfect cube? Well, who's talking to me? X to the third, what else? Right, any exponent that's divisible by 3. Good. So, I don't know that there's really a word for fourth powers. Okay, I think we ran out of them. So perfect fourth powers. What's 2 to the fourth? 3 to the fourth? $81, very good. Then we kind of lose track.
256.
Is it 4 to the fourth?
Yeah, it is.
Okay, then we kind of lose track. As far as fourth powers, x to the fourth, or variables rather, x to the fourth, x to the 8th, x to the 12th, and so on. Have to be divisible by 4. And we'll do the 5th. We're not going to get very far. 2 to the 5th is 32. 3 to the 5th, I'll do it, but 243, just so we're familiar with it, but then we're losing track. And then obviously x to the 5th, x to the 10th, x to the 15th, and so on. So depending on what world we're in, those are the kind of numbers we need to be familiar with. In the first one, we're dealing with the 5th roots of 32x to the 5th. Now, 32 is directly from our list, so we don't need to really break that down at all. And the 5th root of x to the 5th is on our list. So the 5th root of 32 is 2. The 5th root of x to the 5th is x. Do we need absolute values around this? No, because we're dealing with odd power. Okay, the 4th root of 81. 81 is on our 4th. It does have a perfect 4th root, so we don't need to break that up. And neither do we need anything for the x to the 8th portion. The 4th root of 81 is 3. And what's the 4th root of x to the 8th? X squared. Do we need absolute values around that x? Yes, based on the even rule. But why not really? Taylor? Right, you're squaring it anyway. So even if it is a negative number, when you square it, it's going to be positive anyway. Okay? So whether it's positive or negative, you're going to square it, it's going to end up positive. So you actually don't need one there. I can remember in high school asking, because I didn't fully understand it the first time around, I don't think, and asking, well, if I put them there, just in case, would it be wrong? And no, it wouldn't be wrong, but you want to make sure you don't put them in a place where they absolutely should not be, right? Where the answer could be negative, like in those odd cases. And the last one, the biggest perfect cube that goes into 54 is what? 27? 27 times what? 2. So cubed root of 27, cubed root of 2. Then we have just the cubed root of x, which can't be broken down. And the cubed root of y to the 9th. Y to the 9th is right on our list. So we can keep that. So of those 4 pieces, now I can break this down. And I can break that down. So the cubed root of 27 is 3. The cubed root of y to the 9th. Lily J, what's that? Y to the 3rd, very good. Do I need absolute value signs? No, because it was odd. And then what I can't take the cubed root of are the 2 and the x, so I leave those under the radical. Okay, and lastly, I know you did this last year. Rational exponents. Here's the big rule. Whatever the denominator is of your exponent is the root that you're taking. So this is a to the m over n power is the nth root of a to the m. Yes? Okay? So what I always recommend is you can kind of do this in either order. And I'll show you this way. You could do a to the m power and then raise that to the 1n. Or you could raise a to the 1nth first and then to the m power. You know that can happen either way because of our power to power rule, we multiply. No matter which way you do it, commutative property of multiplication says that m times 1nth is the same as 1nth times m. So what makes more sense? This. Okay? Because take this 32, for example. Okay, actually, let's get rid of the negative exponent first. So it'll be 1 over 32 to the 4/5. If you don't have a calculator, it certainly does not make sense to raise 32 to the 4th power, right? So we want to handle the root situation first. We want to take the 5th root of 32 and then raise that to the 4th power. You don't have a calculator, so you want to shrink it before you make it blow up. So the fifth root of 32 is 2. And 2 to the fourth power is 16. So you want to take the root first and then raise it to the exponent. Okay? This is just the 1/2 power. So you could rewrite the whole thing if you wanted as the square root of 25 x to the fourth y to the sixth. And then we have 5. What's the square root of x to the fourth? X squared. And what's the square root of y to the sixth? Y cubed. Okay? Yes. I was going to say, what about, so this one doesn't need absolute values regardless because you're squaring it. But on this one, the square root of y to the sixth, does it need absolute values? This is kind of a tricky one here. We rewrote the problem like this. But originally, what was going to happen if you follow order of operations from the start? What was going to happen if y was a negative number? What was going to happen to it? It was going to become positive, and then when you take the square root of it or raise it to the 1/2 power, it will stay positive, yes? So that will be a positive number. So we do need to put our absolute values around that. You can put it just around the y, or you can put it around the y cubed. It doesn't really matter. Okay? And our last one, if we raise this to the 1/9 power, x to the 6th, this is more of like just a exponent rule, right? Power to power. X to the 6th to the 1/9 makes x to the 6/9. Y to the 3rd to the 1/9 makes y to the 3/9. And then we can just reduce. So 6/9 is 2/3, and y is to the 1/3. You're going to have to, with these, unfortunately, kind of play it a little bit by ear based on what the back of the book says. Because how could I also write this, since they both have a denominator of 3 now? I could write this. So you got to kind of pay attention to what the answer in the back of the book is. You're going to have maybe a multiple choice question, so you'll be able to pick whichever one the multiple choice answer is in, radical form or exponential form. But keep an eye on that because you'll have to just kind of adjust accordingly. All right? Your homeworks are the 1s and the 7s. Quiz coming up on Friday. It's mostly multiple choice. Not sure if that's going to be a blessing or a curse.